What's up? I'm Aryan Das. I study in class 11. You might have seen me in a previous video with Abhay sir, which was featured 2 years ago and was on the Millennium problems. Today I'm back, but with some exciting combinatorics problems. The aim of this session is not just to teach you these problems, but also to show you the beauty of combinatorics. Combinatorics is in general one of the most feared topics in INMO or in an Olympiad in general. But today I will show you how much beautiful it is. So we will have 4 problems today. This is problem 1. This is problem 1. I will not reveal the sources right now, except these sources are there. I will not reveal this source right now. These sources are there. This is AdGauss. This is a very difficult problem to motivate, but sure. This problem is extremely good. This problem is extremely good, and this was the famous. I won't discuss this. I won't discuss question 3 here because this is beyond the scope. I'm just showing you this problem right now, but it's on you if you want to see or not. So let's start with this. Okay, so let's start with this. The problem 1 says that let m and n be positive integers greater than 1. Sure. In each square unit of m into n grid lies a coin with its tail side up. A move consists of the following steps. Select a 2x2 grid, flip the coins in the top left and the bottom right unit squares, flip the coin in either the top right or the bottom left unit squares. And we need to determine all pairs for which it is possible to show that every coin which is head side up, which is tails now, can be head side up. Okay, like for example, consider this. What did I say? It says that there's tail side up. So we have tail, and tail. What does a move do? A move flips these two and tells us to flip one of this two. A move flips these two, tells us to flip one of these two, and so on. We have to find all mn such that all of these tails turns to all heads, and so on, all heads in some finite number of moves. Okay, I would suggest that you give it a try, pause it, and try to see if you find the solution. Okay. The way you should go about this is first try to figure out the answer. Then go towards the solution, because that will be the best approach to this. Okay, I'll tell you the answer. The answer is 3 divides 7. Yes, the answer is 3 divides 7. Now, how would you have motivated this answer? This is very simple. There is a very famous line by Rushil Mathur in one of his classes. What bro said was that in any combinatorics problems, always try the trivial case first. The trivial case here is 2 cross 2 because that's the minimum amount of squares I'm allowed. Okay, so this was the trivial case. So this, as I said, after doing some moves like TT, from here you get to like H, T, H. From here you get to like T, H or something, or like T and so on. But now to H. So it's like you see some parity things are happening, and this is not allowing all heads. So 2 is not the answer. What about 2 3? Okay, sorry, this is a 3 cross 3. I wanted 2 cross 3. So for a 2 cross 3, what we will do is, suppose we have tails. If we first select this 2 cross 2, and then write heads here. And there is a trick. What we do is select this and turn this to heads. Okay, now we select this 2 cross 2. This we choose 2 heads. and now this we will choose and we'll turn it to heads. As you can see, all heads are. Similarly, now you can say, okay, and why anything? If I just continue it with again a multiple of 3, then also this will happen because I can just delete this, right? Okay, and then I can continue. Again, I can continue. So, okay. Similarly, if I go down, if I go to a 3 cross 2, okay. And I guess you know what does M cross N mean. M means the number of rows and N means the number of columns. Where this is the column and this is a row. Or like if you say these are rows, these things, and these are columns. Okay? So when we have a 3 cross 2, a similar reasoning shows that suppose we have tails, a similar reasoning. We turn these two to heads and we choose this one to turn heads. And we turn these two to heads and we choose this one to turn heads. Shows that 3 cross 2 works, and similarly any 3k cross 2 works. We also have 2 cross 3k works. Okay. The next thing which I want to show or want to achieve is, does a 3 cross 3 works? If a 3 cross 3 works somewhere. So when how we will show this? Okay, it's not not hard, but also it's not easy as well. So I'm just shifting these problems down. So let me just shift these problems down. 1 second. Yeah. So so the next thing which I want to ask myself is, does a 3 cross 3 work? So for that, what I can do is just try, because I have nothing else to do. So there should be some patterns here, right? There should be some patterns here which I can do. The first thing, of course, I need to change these two heads. Now what's happening is that, what if I change to this heads? Okay, this remains same. So this again changes to all heads. This is changing, but now notice something does not add up here. This is like head tails, and something tells me that the parity would disturb me a little. Yeah, okay. Something tells me the parity will disturb me a little. If you want to see how it will disturb you a little, I will just show you right now. When you just check these two, this will flip to something like this. Or suppose you have this, you flip this to heads, and then this is isolated. I'm using some vague English terms here because that's what combinatorics is about. You use some vague English terms to define what problem you are having, and then you try to turn it into mathematics. Okay, so I will just keep on trying if a 3 cross 3 work. Okay, and let me give you a hint on whether it works or not. The hint is, yes, a 3 cross 3 works. And of course it should have been obvious by the answer, but now we don't know the answer. We're trying to develop the answer. Okay, a 3 cross 3 works, but the construction for a 3 cross 3 is a little difficult. So there's a very clean idea in combinatorics that's called assigning binaries. what does this idea is this is it's purely representation. This is purely representational. This is purely representational. What does it say is that whenever you have heads or tails in a problem, always represent it with zeros and ones. Whenever you have heads and tails in a problem of combinatorics, always represent it with zeros and ones. This will help you in many cases. The first case it will help you is that you will introduce numbers. You will introduce numbers to heads and tails. The second thing is that increasing or decreasing binary sequences, increasing or decreasing binary strings. There's a very famous movie called X+5. This is the only movie made on mathematical Olympiads. There was a question regarding cards in that movie, and the solution was using this binary. It was like if there's heads up and heads down, and the student, what he did was he represented heads up by 0 and heads down by 1. And there was some process happening, and you had to show if the process terminated or not. And what the idea was that with the process, every time the binary, which was this binary representation of the strings, always decrease. So it could not go negative, so it will reach 0, and then at that time the process will have terminated. So yeah, this is like lore, but you don't need lore right now. You need a solution to this problem. Actually, you don't even need a solution to this problem. You need the feel of this problem, why this should be true, and how are we even getting to what we are getting right now. So I will give you some time, pause and find out the construction for 3x3, and I will see you at that time. So I think you have tried your best. So I will give you some idea, okay, on what can happen and what should happen in this. So again, this is idea number 2 in problems like this. The second idea, the second idea in problems like this is very simple. It's like spam. Okay, now what do you mean by spamming? Spamming is a very interesting idea because it has a lot of story. Spamming could have been used in a very famous ISL, which I will be showing at the end of this video. Spamming could be used in this problem. Spamming could be used in a lot of construction-based problems that are based on invariance. And all of those construction-based spamming problems are due to find a construction after which the invariance will be used. Okay, so that's the idea we'll use here, and it's a very normal, commonsensical idea that I will introduce this idea to you. But this is a very commonsensical idea. What is the idea essentially? Is that suppose you have a 3x3, right? So know that you know how to solve a 2x3. You know how to solve a 2x3. So if you somehow are able to get rid of this, like turn this into all heads, the first row into all heads, you're done. Then you know how to solve this. If you're able to do one row into all heads, you're done. Also, if like this is for like 2x3, if you have m cross 3 or m cross 3n or 3n cross m, any of these configs, what you can do is you can turn the first row or the first column as all the heads, and then you can keep spamming it till you get a 2x3n or you get a 3n cross 2. And as it's like one row, you can just spam it m minus 2 times, and you will be getting 2 rows. This same algorithm m minus 2 times, and you will get 2 rows, and you will get this and this. I will show you this. I will show you this in action today. Okay, so this is essentially the idea. So for now, what I want to do is get this a 3x3, this 3x3, and what we'll try to do is, as I said, we will have to somehow show that we can reach all heads in this, all heads, and then we can just remove this and we can just go with a 2 cross 3 and we are chill with the 2 cross 3, right? So yeah, so again, as I said, the binary assignment, we let us assign heads as 1 and tails as 0. And now you are thinking that okay, this is purely representational, I may or may not do it, but my friends, you are in for a surprise that this is not purely representational. This is a crazy surprise which is coming up. This is not purely representational. Okay, so take my words and let's take heads as 1 and tails as 0. So what we'll do, as the tails are 0, so this is first filled with entirely with tails. Okay, now what we will do is try to fill a construct. We'll try to construct such that this turns into 1 1 1 0 0 0 0 0 0 or 0 0 0 0 0 0 1 1 1. Okay, one of this. Okay, or it may also turn into 1 1 1 0 0 0 0 0 0. Okay, now how it turns out is that there are two different configs. Okay, there are two different configs. So what I will show you is just config 1. In what it happens in config 2 1 is that this happens. Config 2, what happens is that this happens, and this is just somehow a mirror image of these. Okay, so I will just show you config 1. Try to figure out config 2 by yourself and drop it in the comments. Okay, so here is config 1, and again, this is just a play thing, and this is in no way easily motivated. You need to play around, continuously play around, and then you will find this. Okay, so let's start. What we will do is, first we will take this. I will also show you here which ones we are taking. First, sorry, my bad. Yeah, sorry. Yeah, we will also show you which ones we are taking. First we will take these 3. Okay, and we will turn them to 1 1 1. Fine. Now what we will do is take these 3 and again, of course, turn them to 1 0 0. Now what we will do is take these 3 and turn them to, you guessed it, 1 1 1. Now what we will do is take these 3, actually not these 3, these 3 and turn them. And how will we do that? Yes, brother, you guessed it. This will be 1 1 0. And final nail in the coffin. As you can see, this is 1 1 1. What we want, 1 1 1 0 0 0 0 0 0. And as the luck of God will have it, we can just take these 3. Then we could have just taken these 3 and we would have gotten, sorry, yeah, we would have gotten 0 0 0. And damn, brother, damn, we found this config. Yes. Yeah, and now what we will do is just spam this. Okay, so suppose now I will show you the power of this. Okay, suppose you have this extremely big something. Okay, yeah, something extremely big like this, and then you have like many. Okay, 1 2 3 4 5 6 7 8. So you have 9 here, and 1 2 3 4 5 6. You have 6 there. So what you do? So you have 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0. My god, oh my god, oh my god, this is so, this is such a task. Yeah, so this is a 9 into 6, or yeah, all we call it 6 into 9. We are very strict with our standards and our notations. What we will do here is use this to get 111. Again, use this to get 111. Use this to get 111. Okay. Now what we will do is simply and easily what you will do is just delete this row. Do you see an inducted down version of the same problem? 111, sorry. Yeah, this is like stroke. Yeah. 111, 111, 111, 111. Yeah, and so on. And you keep inducting down, keep removing this, keep removing this. And when peak struck is that when you're left with this. And by a miracle, you know how to solve a 2 cross 3k. And this was the power. You spam, you keep spamming, and you will be done. Now comes the most important part of the entire question. The part that made this question one of the best questions I've ever did. Although that may be a very big exaggeration, and that part is called proving mn is not equal to 3k does not work. Now for this, I will give you some lore. Okay, always, I already gave you a hint that invariant works because what we did was spam, and as I said here that spamming invokes invariant test problems. So what we will try to do here is do some invariant shit here. Okay, so what we will do is, whenever in general in a combi problem, what you always should do is try these three always: invariance, coloring, and parity. And crazily enough, we will be using all three in this problem. Are you ready? Okay, I will ask you to take this hint, pause the screen right now, and try to work it out. It's extremely interesting. Okay, I will not reveal the answer and I will not reveal the solution. What's happening essentially is that we are trying to color it in such a way that we will take advantage of the process. What's the process? Suppose you have like 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, and 0, 0, 0, 0, 0, 0. The process that's happening, if you take this, these two are changing and one of these two are changing. So what I want in an invariant-ish setup is that when these two changing, these two are different colors, and when these two changing, these two are the same colors. So that only one changes. So yes, and there's a solution. What we do is we select a cyclically forming section where this is RBG. Now what we do BGR. We cyclically shift it, and we cyclically shift it again. GRB, GRB, GRB. We cyclically shift it again. Now there is the stuff. Remember what I said about binary representations? You will see its use here. Represent or define the sum of a color as the sum of numbers in its cell. For example, 111, 0, 1, 0 will mean R has 1, blue has 1, and green has 2. How? These are the sum. I mean the sum. How? This is R, this is B, this is G, and this is B, this is G, this is R. So R is 1, B is 1, green is 2. Okay, you understand what the sum is. Now note the following. Okay, now note the following. What's happening is that in any of this, what we can do is that we can divide this into 3k into S plus a 2 cross 2, a 1 cross 2, or a 2 cross 1, or a 1 cross 1. Okay, we can divide it into, like, suppose this is like this, and we add this cell extra. This is a 3 cross 3, and this is a 3k S. Okay, Now what happens is that, what if I have this extra? What if I have a 4x4? Is essentially my question. What if I have a 4x4? Is that according to this I can divide a 4x4 in a 3k here, this 3 strip, this 3 strip, and you're left with a 1x1. So that's what I'm saying. 3k into S, or else you will have a 2x2, you will have a 1x2 or 2x1, or you will have a 1x1. Okay, in this case we had a 1x1. If you take a 5 into 2, take a 5 into 2, okay, this is 3, this is 3, this is a 2x2. Okay, so we can divide it as I showed you. Now what will we do with the division is that in a 3k into S, the number of, okay, by the way, R represents red, of course, if you didn't understand, B represents blue, and G represents green. Okay, let the number of red in this entire setup be X, Y, and Z. Like X is the number of red cells, Y is the number of blue cells, and Z is the number of green cells. Note that in 3k into X, X is equal to Y is equal to Z. Yeah, in a 3k into S, X is equal to Y is equal to Z, because it's cyclically there. So in any cycle there is RBG, all three, like you can see. In this cycle there is RBG, in this cycle also there is RBG. Okay, and even in the diagonal there is RBG, but that does not count. Okay, so this is how this is such an interesting coloring. Okay, now what's the main problem here is that in a 2x2 you will have exactly X, Y, Z, all three increasing according to your coloring, but also one more of among X, Y, Z increasing. So you will have one of these cases. Where in this case X will be equal to Y plus minus 1. In this case X will be equal to Y plus minus 1, and in this case Z will be is equal to X plus minus 1. Okay, you get this point? Wait, sorry, this is not the case. X is not equal to Z is equal to Y. Or did I not do this already? Yeah, no, I didn't do this. Yeah, like the non-equal part is distinct from these equal parts by at most one. How is this proving? In a 2x2, note that XYZ is increasing by 1. In a 3ks you have XYZ and all of them are equal, but in the 2x2 XYZ is increasing by 1, but one more is increasing because you have 4 colors, and by PHP one more is increasing. In a 1x2 or a 2x1, note that you have one less color, like you have 2 colors increasing, only 2 colors increase. Only 2 colors. You have this as 2x2 or you have this as 2x2. So either RB increase or like RB is like this. So see, green does not increase. So green is deficient. And in a 1x1, only one color increase. So that's excess. So you get the one point. In 2x2 there is excess. In 1x1 there is excess, but in 1x2 and 2x1 there is a deficiency of a color. That means from here what we use, we mix all of these together and come to this conclusion. In a process, what happens? In the cyclically driven process BGR, when you take this and this, the sum of this changes, and also the sum of one of these changes. So the sum of all 3 colors changes in the process. But that means starting was 0, 0, 0, 0, 0, 0 and so on for all colors. So that means they had the same parity mod 2. That means at the end, because the process does not change anything, they should have the same parity mod 2. But note, due to this, there is an excess color. So that means that will not have the same parity because there is an excess color, right? Here we have same parity, but here we have the excess color, and that breaks the invariant. And this implies that color does not have a head. When all others have a head. Okay, and that means this condition is broken and we are done. Okay, now this was so interesting. We find out a construction, we do this entire invariant thing, and then we come to the conclusion using all 3. of what I stated here. All three of what I stated: coloring, invariance, and parity. So this was an amazing problem. I love this problem. So this is it. Okay, I also will show you the EOPS version of my solution, and also show you the problem which inspired my solution to this. Are you ready? So yes, this is the EOPS solution. This is I go by mathematical RKS in EOPS. Yes, so this is the answer is 3mn. Then this, yeah, so this is the config 2 if you were wondering. This is the config 2, and this goes like this. And yeah, this was a great problem, and it was very motivated. This was very motivated, and the problem which was inspired, this was inspired by, is this problem, and it is IMO 1993 P3. Great problem. I would encourage everyone to try. And this problem, by the way, if you didn't notice, is 2023 C1. So yeah, that's it. So I didn't do these 3 problems right now because I don't know if I taught very nicely for you to appeal to you guys. This was my first lecture. Please drop in the comments if you want a part 2, and if you want a part 2, I will put this. I will also make a session on these 3 problems. And if you don't want a part 2, I won't. I will try to improve my teaching then. But thank you for tuning in. Thank you. Please drop a like.